Hello, good morning. How's it going?
Hi, Professor. How's it going?
Hi, good morning, everyone. Okay, I hope you're doing good today. So we have talked about Newton's first and second law. We spent quite a lot of time on working out different scenarios of problems of Newton's second law. The last law in dynamics is Newton's third law, and this is what we're going to discuss today. And we're also going to look at centripetal force. I've already talked a little bit about it, but we'll spend some time working on the uniform circular motion and the force that's responsible for that motion. So Newton's third law describes a action and reaction pair. So it says if a force exerted object A by object B, then there must be a force which is equal in magnitude but opposite in directions by object B on object A. So they are equal in magnitude but in opposite directions, therefore we have a minus sign. Okay. So for example, if I push the wall, me exerting a force on the wall. So Newton's third law will say that the wall at the same time exert a force on me that is opposite in the direction I'm pushing, but equal in magnitude. So if I push the wall harder, the wall will push back on me harder, but just in opposite direction. So that's Newton's third law. Notice that these two forces are called an action-reaction pair, but they always act on different objects. It's not on the same object. The force I push to the wall is acting on the wall. And the force from the wall pushed back at me is acting on me. So these are talking about a pair in different objects. They're not going to appear on the same free body diagram because they are on different objects. Okay, so we can use Newton's third law to explain quite a lot of different phenomenon. There is a demo that shows, and I hope we will be able to explain using Newton's third law. So let's go ahead and take a look at that demo.
My job is to make college.
All right, that was so jumpy. Okay, let me replay it. So you notice the first thing, that's something we're all familiar with, it's probably not surprising to see, is the fan switch was turned on and the fan starts moving. Can we explain that using Newton's third law? Anybody would like to give it a try?
It's kind of like how rockets work.
Okay.
Like how they kind of just like throw mass out of the little hole at the bottom to go up, because the air is by the what's it called? By the little fan. It's moving the air towards the fish on the screen, like in that direction. So the mass is the reaction force, and that's pushing the mass to the left side of the screen.
Very good, thank you. That's exactly how we can use to explain how rocket works. In the fan demo scenario, the fan pushed the air to the right and the fan itself moving to the left. So they have a little screen. They mounted the screen on the fan. Well, that was just blowing on the car. That's not so surprising. But they're going to turn the switch on. Okay, noticing that now the card is not moving. And why is that?
The air is now being blocked from basically being thrown back, so it can't move forward now.
Yeah, the air is now being blocked by the screen and cannot continue to go that way. Another way to view about this is we can view, in this case, you have the screen, so the air in between the fan and the screen, you can view this entire thing as a whole system. You can view the card and the air in between and the screen as an entire system. So whatever happens within themselves is now part of the system now. And yes, you can have the air pushing on the screen, and you can have the air that's sort of bouncing back from the screen pushing the fan. But whatever they're doing now, it's part of the entire system and is not going to change the acceleration of the system. Okay, that's just a slight deviation from what we saw earlier. There's a little more parts about the demo, but I'll save that for you to view yourself later. So let's go back to our discussion. I was going to say that this is similar to how does a rocket work by the Newton's third law. The gas molecule that's been pushed downward by the rocket will exert a force equal in magnitude, but opposite in directions, as you can see, push the rocket upward. So there's a question, natural question is, do rockets require air to accelerate? Could they work in vacuum? So you can say that, well, the air is being carried by the fuel by the rocket themselves. So even though you are in vacuum, like you're in space, of course it can still work, right? We have all the spaceship that still works in the space, in vacuum. So now you already know everything you need to know about Newton's third law. So let's see if we can actually use it correctly to answer questions. Here is a question. It doesn't require much of discussion, so I'm just go ahead and let you vote on it. Okay, you can take a moment to read, and after the words, feel free to put in your thoughts. All right, let's go for another 10 seconds. All right, any last minute votes? Any more votes, thoughts? Okay, let me go ahead and close it, and then let's take a look at our results. We're pretty much equally tied between choice A and choice C. B certainly is not so much of a distractor. It seems like, or feels to me, to everyone, that a small guy might experience a larger force. So since we are under the topic of Newton's third law, do you think that is helpful here? Or you may have some intuition from our experience, but do you think Newton's third law can help you navigate that intuition?
I think once you gave an example about like the fly and the big van or truck on the highway, How like the little flag, because of its mass, will get all squished up, but we won't in the car because we weigh a lot more. Well, our mass is a lot more. So I think I chose C, but I might be wrong. But the little guy, he has like his his reaction force. So the small arrow but pointed in the opposite direction, and he has the big arrow from the big guy. And then the big guy has the opposite, the little guy's arrow and his reaction arrow. So that's why I think they're the same overall in terms of magnitude, not direction.
Yes, so this is asking about the force. The word average is really just saying, well, this collision force is messy, but let's just say on average how big it is. It may not be a constant. It may be a little bit bigger at this instant, a little bit smaller, and then another instant. But let's just say on average, what is the force during the collision? Now, if we're applying Newton's third law, we will view this as object A and object B. If A exert a force on B, then B exert a force back on A with the same magnitude, it says, and opposite direction. So which means they should experience the same force. As far as our intuition, if I ask you another question, instead of asking what is the average force during the collision, I'm asking which one experienced a bigger acceleration during the collision. Which one do you think that is? So I'll open up for voting again. So everything stayed the same, except I'm now asking who experienced a bigger acceleration during the collision. Okay. Now we're talking about the horizontal direction, of course, because gravity and normal force, they in the vertical direction is balanced for both of them.
Professor, sorry, would it be possible for you to go to the rocket slide again for a quick second? I forgot to take a picture and I couldn't write fast enough.
Okay, 1 second.
Okay.
I'll come back right back. 1 second. I'm switching the slides. One second.
Thank you. I got it.
Hey, Professor, can you
Yeah.
re-explain? Can you re-explain the last one? Why they had the exact same force?
Why do they experience the same force? Okay, so let's say this is object A, this is object B. Newton's third law saying if object A exert a force on object B, then object B must exert the same force on object A that is the same magnitude, but just simply opposite directions. So what force they experience during the collision is really just from the other person. There's no other object out there to exert this force on them, right? So the force, the object A, which is the little guy, he feels, the force he feels during collision is from object B, the big guy. Now let's say little guy bounce into big guy and exert a force of 500 newtons. Using Newton's third law, that says the big guy must exert the same amount of force, which is 500 newtons, but just simply in the opposite direction. So little guy experienced 500 newtons, big guy experienced 500 newtons. So they have the same force during collision. Is that clarified?
Oh, yeah.
Okay, so that's really just a direct application of Newton's third law. What we are doing right now is to reconcile that with our intuition, because our intuition feels like gotta be make a difference for them, right? So let's take a look at our votes. I'm going to go ahead and stop it now, okay? In terms of which one experienced a bigger acceleration, now you may, okay, we do have quite a lot of voting for C. They experience the same acceleration. But how do we get acceleration? Acceleration is equal to the total force that's acting on an object divided by, what should I divide it by?
Mass.
Mass. Very good. This is Newton's second law, right? So I already said, we already established, they both experience the same amount of force, which is the collision force in the horizontal direction. Gravity and normal force balance out, so you don't have to consider that. Now they have the same force, 500 newtons. And do they have the same acceleration? Well, that depends on, do they have the same mass? So whoever have a smaller mass is going to have a bigger acceleration, right? So in this case, which one have a smaller mass?
The little guy.
The little guy does, yes. So m is smaller for little guy, which means acceleration is bigger. So the acceleration for the little guy is going to be much bigger than the acceleration the big guy feels. And that's why in real life, you do have different consequences, even though the force is the same, but the effect is different. Okay, so A is correct here. So I hope by this question, we're able to reconcile our intuition with physics laws. So we can build upon what we already know and know how to apply it correctly. This question I'm not going to do because it's probably something you have already seen, is carry this intuition to an extreme. Okay, so now we're talking about the car and the bug. Real life is the bug will be totally smashed, whereas it doesn't make any difference for the car. Okay, so when we're asking the force between the car and the bug, okay, so there's still no doubt because Newton's third law, which means if the car exert a force on the bug actually exerted the same amount of force on the car. Let's say it's 5 newtons. But 5 newtons is so big for the bug, it's enough to smush it. But 5 newtons on the car is nothing. The car barely get affected at all and continue to go, right? But the force is the same. The car exert the same amount of force on the bug as the bug exert on the car. So that is carrying that extreme different scenarios. But you know, using Newton's third law, that must be true, right? They just have a different effect on different objects. Let's go to recall a elevator question, because when we were doing this problem earlier, I simply gave you a hint. I said, well, the measured weight that show up on the scale as you were standing in the elevator is the same amount of normal force acting on the person. I didn't explain why, but now we can. Okay, so let's look at the normal force acting on the person. It's upward, and this force is acting on the person. So this is on person by who? By the scale. So using Newton's third law, then the person must exert a force back on the scale. So this be a force by person on the scale. The person is pushing down on the scale. So the scale is providing a force back on the person, which is opposite in direction. So that's upward. Normal force is upward. Okay. So that's why the normal force on the person is the same as your scale reading, because the normal force and the force you push on the scale are action and reaction pairs. They act on a pair of different objects, one on person, one on the scale. They are equal in magnitude, right? The force by the person on the scale, so how hard you push on the scale is reflected on your scale reading. So if it's 100 pounds, then that reads on the scale 100 pounds. So that's why whatever you are reading on the scale is the sensor of the scale picking up how much force you are pushing on the scale. But Newton's third law says that is the same as a person, a normal force acting on a person. That's why these two are the same. That's why when we are asking about what is the scale reading, you can go ahead and calculate normal force instead. They're not the same force. They act on different objects. They do not appear in the same free body diagram. They appear in two separate free body diagrams because they are on different objects, but they are the same in terms of their magnitude. Okay, so that is the reason we were able to do that for the previous question, because there is another layer of the Newton's third law that we applied in here. So any questions about the elevator problem? Any questions so far?
Sorry, I got cut off a little bit. So essentially, you're saying that the magnitude of the force is equal to the magnitude of the normal force, correct? But it is
the magnitude of the force on the scale, yes, is equal to the magnitude of the
normal
force on the person.
Oh, okay, gotcha. Thank you.
It's different objects. So we will continue to look at another example that can help us clarify the different pairs of interaction. So let's look at this question. Okay, so we have 3 books staying at rest on the floor. They're stack up together. Now we want to draw a free body diagram for book A. So before you go ahead and do a discussion in the breakout room, I want you to be reminded what are the steps of drawing a free body diagram. You want to first isolate the object you're interested in this case, object A, and then think about all the other objects that A is in contact with. Okay, has to be directly in contact with, except gravity. Gravity, you do not require a contact. Okay, so take a screenshot and let's take a minute or two to have a discussion, then we'll come back to vote. I will come back. I have drawn down one side of rotation. Today I'll visit breakout room 1. Okay, I know it's different people every time, but hopefully by doing this enough times, I get to talk to everyone.
And we need 1 upward force at minimum, right? So since we need the 2 downward forces, oh wait, did I say that right? Yeah, on A, we need the 2 downward forces and then the normal force from the floor, at least. So I think it's either E or D, but none of them appear to be gravity based on their length. So I think it makes sense that it's E.
I agree. I think the E makes the most sense because B also has a force that's going to be pushing on it, and you're still going to need the normal force. So I agree to what you're saying about how you need 2 pointing down, and D doesn't have the second arrow pointing down.
And A has, I think, too many downward forces, because I don't think the largest downward on A is large enough to beat gravity given the size of the normal force. What do you think, Professor?
What do the rest of you think? Musa and Bachi? Did I say that right?
It could be, yeah.
For you agree that it's going to be E, 2 downward forces and 1 upward?
Yeah.
Okay, so are there any forces we can identify? We know there's always gravity, so there's gotta be 1 downward. There you go. There's another downward, and what would that be?
Sorry, for clarification, I thought you said on the free body diagrams we didn't have to do gravity.
Oh, we always do gravity.
Oh, okay, so then.
Oh, when I
Then it'll be
say
A.
don't do gravity is when you're on a ramp, you draw
Oh,
you break
okay.
it down into other components and you kind of cross it out, but you still show that you have considered it.
Okay.
Okay. What's the second force downward?
Well, if we are including gravity, then actually I think it may be A or E depending on how you want to combine forces. Yeah.
What do you mean combined forces?
So if you consider the downward force on the book from from C and B on A, if you combine those as one force, then C could be it. But A, I think, makes more sense now, maybe because you have the downward force of gravity like in the middle, because A is physically the largest, and then we have C, the downwards of C, and then we have the downwards of B, and then the upwards normal force from the floor. But if we're only doing what's in contact with A, then it would be E again.
Yeah, so when we say C pushing on A, noticing that, yes, the effect of having just one book on A and the effect of having two books on A certainly make a difference. But in terms of your drawing, that which one does A have direct contact with? A never touches C, so C cannot push on A, okay? It has a force pushing on A, but that's through B, and you can only get that force through the contact between B and A. So you can say a downward force pushing down by B, but we cannot really draw one by C, okay? Because C does not touch A. So that's I think I know what you mean. You mean C has gravity, yes, but C do not directly push on A, and therefore we cannot draw that arrow. It does influence how big the force from B though, make that a little bit bigger, but we cannot draw a third arrow. So yes, two down and one upward by the floor. So actually your original intuition is correct. Very good. I'll see you guys in a little bit when we go back. Okay. All right, please go ahead and put in your vote, whichever free body diagram I think is correct. Okay, any more votes? Let's go for another 10 seconds, okay? If you haven't voted already, please do so. All right, okay, I'm gonna go ahead and stop the vote. And let's take a look. We do have quite a lot of a spread across these different answers. Looks like maybe A and D are slightly more than the other ones. So I'm glad that A, D, and E, the ones that you all agree on, has one upward arrow. What is that force? The one upward arrow on A. What is that upward force?
The normal force?
The normal force on A, very good. And that normal force on A is provided by which object?
The surface it's resting on?
Yes, normal force by the surface, by the surface. Excellent. And A, D, E, at least one of them has a downward arrow. And what would that be? We can name one downward force.
Gravity.
Gravity, there's always gravity, and you do have to always draw it. It's gravity acting on A. So yes, one of these, at least one of these has to be gravity. And now the question is, are there any downward forces on A? Any other downward forces? Free body diagram asks us to isolate the object and look at which other object this object is in contact with. A is touching the surface. A does not touch gravity, but gravity is a long-range force. Any other force requires touching contact. A is also in contact with
The book B?
B. So B must be exerting a force on A. And would that be upward or downward?
Downward.
Also a force by B. So that's it. That's all the three forces. The book C, you say, wouldn't the book C have any effect? The book C does not directly push on A. It does push on B. So it may affect how hard B push on A, but we do not draw a separate force from C. C does not push on A. So correct answer is E, 2 downward and 1 upward. So I want to show you the different action reaction pairs on all of these books. So let's do that by looking at its animated slides. So let's look at book C. Okay, book C, if you draw the free body diagram, C has 2 forces only. One is gravity, one is normal force. Gravity provided by the earth, normal force is provided by B. B is supporting C, right? So you have those 2 forces. Okay, now if you draw a free body diagram on B, you have 2 downward and 1 upward. The one of the downward force is B's gravity. Another downward force is the force pushing on B by C downward. And the force supporting force upward is the normal force on B by book A. Okay, so now we can label all of them. Okay, so all of these labels. Now the third one is book A, and we already talked about 1 upward is by the floor, and 2 downward is, one is gravity always, the other one is normal force. The pushing force is also a normal force, even if it's not upward. Okay, so now if you don't feel comfortable, you can call that the force by B on A or the force by C on B, but it's still a normal force. So now let's identify the action and reaction pairs. So these 2 are action reaction pairs. You can see one of the force is by B on C, the other is by C on B, okay? B on C versus C on B, these are a pair. Are there any other pairs here? Well, the normal force by A on B and B on A is another pair. These 2 are a pair, the 2 dashed ones. So you can see that they come in pairs, but they're in different free body diagram. They do not never appear together. Okay. There are also action reaction pairs by all of this gravity on Earth. At the same time that Earth is pulling on all of us, we all exert the same amount of force on Earth. The gravity affects us deeply, right? When you jump from a height, you fall because of gravity. But these forces on Earth, it does not do anything to the Earth because Earth is so massive. But doesn't mean that force doesn't exist. All of these has a third law pair. So all of these objects, including every one of us, is pushing on Earth with the same amount of force that the Earth is pushing on us. Okay, so I didn't draw the free body diagram for the floor, but if you draw it, there is a action-reaction pair from A to the floor. So A by A on the floor. So that's just a animated slide to show all the different free body diagrams. Okay, so next, I'm going to talk about circular motion. As we are on the slides, I'm going to simply advance. This is a summary of Newton's laws, but you could read that on your own. I'm going to go ahead and move on to talk about circular motion and centripetal force. This is the last little bit of information we're going to do in the dynamics chapter. Well, after this, we will move on to talk about energy. Okay. So we already said previously, if you have a circular motion, we definitely need a centripetal acceleration to change the direction of the velocity, and there must be a centripetal force. This force is named after its effect. It's not a new type of force. Different scenarios have different forces playing the role of the centripetal force. Now, for example, if I'm taking an object and tie it to a rope, and I swing it around. So in this case, what is the centripetal force if I'm swinging an object around? What kind of force is providing the centripetal force in this case? What do you think? And Jacob said it's tension. Yes, very good. The string attached to the object provide a tension pointing toward the center, and that is your centripetal force. It's not a new force, it's tension. So you don't draw, if you draw the free body diagram, you say tension, but you do not draw again centripetal force. They are the same force. Now, how about when the moon is orbiting around the Earth? It's a circular motion, roughly. And what kind of force is providing the centripetal force for the moon? It's the gravitational force, very good. It's a gravitational attraction between the moon and the Earth. So the gravitational force is a centripetal force that is keeping these different objects on the circular motion path. And our planets and all the other planets orbiting around the sun. So the centripetal force is provided by the gravitational attraction. And we'll talk about gravitational force separately in a different chapter later on in the course. And we talked about this already. Now, in the case of a car going around a ramp, you need a centripetal force, and which force can provide that? That is a force provided by the friction. The friction is provided between the tire and the road. So your car, the tire pushes on the ground, and the ground gives the car a friction, static friction, that is pointing toward the center. And friction is playing the role of centripetal force here. So in different scenarios, the centripetal roles is being played by different kind of forces. So you can think of, I have all these forces, and in this case, this force wears a hat of centripetal force. In another case, this other force wears a hat, but it's the centripetal force itself is not a new force. So this is a slide you have already seen from the previous course. Now let's look at this particular question, okay? So let's say you're in the roller coaster, and some of the roller coasters, you go vertically upward at some point, go all the way around. So what is the free body diagram on the roller coaster, on the cart? Well, a person along with the roller coaster are the entire system. So what is the free body diagram that you draw at the top on the system, on the person, or on the cart? They're together. Okay, so let's take a look at this question. Couple minutes and to discuss, and then we'll come back for this one together. So take a screenshot and then accept the breakout room invitations. Hello, how's it going here?
Hello.
Hello, Anhal and Arturo, Marcus, and Summer. So any thoughts about this particular question? We're not seeking an answer yet, but more like you feel free to discuss it together. Like I can think out loud while I'm here.
So would it be gravity for sure because it's on top, so gravity's pulling it down?
Yes, there's definitely one downward force, that's gravity, okay?
And then when
Does, Professor, does the length of the arrow matter as well?
Yes, there is a difference in terms of velocity, but that's not going to affect our free body diagram. So the length of the arrow indicate how fast your roller coaster is going. It's a little slower on the top and a bit faster on the bottom. But when we draw the free body diagram, it's not on the top, it doesn't matter.
Oh, no, it's because like I was thinking E and B, but the arrows are
Sorry.
different.
I thought, Summer, you were asking about the length of the arrow of the force. I'm sorry. That's what you were asking, right?
Yes.
The length of the arrow, yes, I think it does matter if the two forces are in opposite directions, but doesn't balance out, then you know there's a net force in the direction where whichever the arrow is longer. If they're balanced out, which means there's no net force. So yeah, the length does make a difference. And I'm sorry, someone had another thought earlier. Was it Marcus that you said something?
Oh, no, I was just saying that was E or B, but the arrows are different lengths.
You were thinking B, right? They're different
Yeah.
lengths. So is B correct?
I was thinking B as well, but I was thinking B or E.
B or E, okay. So this is a circular motion. This is a circular motion. And we say centripetal, this is the center of the motion. You need a centripetal force. And do we agree this person, this cart, need a centripetal acceleration pointing toward the center. So you do need a centripetal force provided pointing toward the center. So whatever force at the top, it has to have a net force pointing toward the center. Does B give me that? E gives me these two cancel out. No force in that direction. These two gives me a force in that direction. That now would indicate a circular motion sort of at this location. Then you're pointing toward the center. The center is here, but the circle is over here, right?
So it has to be C?
It has to be C, yes. And other than the one force, we can figure out what that is, the gravity of the object. Now, in any other forces, you have to have contact. Think about it. Now, the only other object you're in contact with is the track. right? So the track is pushing on the roller coaster. And in which direction? Is the track pushing down on you, or is the track dragging you upward? Which direction?
Isn't it pushing on you? Because like you're kind of like pushing on the track.
Yes, you push on the track pushing on you. Very good. So these two forces together provide a centrifugal force. Excellent. Thank you, everyone. Let's go back. We'll go ahead and discuss more over there.
Okay, thank you.
Thank you. All right, 10 more seconds. Let's wrap up our voting. 10 more seconds. All right, any last minute vote? Let's go ahead and take a look. I'm gonna close this. Looks like E is the most popular, and the next one is C. A and B are tied. All right, so we all know there's gravity, so I'm glad we identified that, of course, in all of the different drawings. And instead of the C and B, the difference is, well, C shows another downward force and B shows an upward force. So let's say, well, for the diagram, we identify in what other objects this cart is in contact with. Cart is in touch with the track. So the track is exerting a force on the cart. Do you think that force is downward or is it upward? Is the track pushing down on the cart or is the track lifting up the cart? That's the difference between C and E. Thoughts?
I can. Oh,
Sorry.
you can go.
Is it keeping it up? Because it's being like the cart's being held by the track and it's upside down. Like, yeah.
So would you say when we go really, really fast, you kind of like the cart is pushing on the track. You want to have a close contact, right? So and then in reaction pair, the track will be pushing down on the cart. So think about, you have the ceiling in front of you. If you push on the ceiling would be pushing back on you. So the force from the track is actually downward on the cart, other than the gravity. So there are two forces down. One is normal force from the track, the other is gravity. Now we feel like we need a lift force in order for the object not to fall, but because it's in circular motion, it's not going to fall, right? This force that you provided is going to give you a centripetal force that serves as a role of changing the direction of the velocity. Okay, so yeah, so it's not going to fall. That's why when we have these planet orbiting around the sun, it's not going to fall toward the sun because it has enough of a velocity that force that's going toward the center is providing the role of a centripetal force. Okay, so so C is the correct one. Think about what kind of acceleration you need and what other forces you're in contact with. And the only chance that you might fall in real life is not really just simply as there must be some other mechanism. But if you have sort of a marble rolling around a circle, right? The smallest forces that you can have is when the normal force goes to 0. So when you're barely hanging onto the track, then in that case, normal force goes away. But in no ways where your normal force is upward, is always pushing down on you. So the answer here is C. It serves as a centripetal force. Now we could further to do a calculation in order for it to not fall off, what is a minimum speed required? But we don't have time to do it now. We will try to finish it up at the beginning of our next class. I encourage you to think about it and we will finish it next time. All right, so that's all we have for today. We will wrap this up and also we start doing energy on Wednesday. Have a good rest of the day. Bye, everyone. I will see you guys next time.
Professor, could you go back to the slide that was at the beginning of like the centripetal force discussion today?
Here?
Yeah, up one more, please.
Here?
Okay, that was okay, cool. I got all the
cover
notes then.
page.
Yeah, okay, thank you.
Sure.
Have a good day.
Have a good day yourself.
Thanks, bye.
Jacob asked, so is inertia what we feel when we feel squished as a car zooms upside down on the loop? You feel squished because as I said, of that velocity, you are pushing on the cart, right? So and then you feel that. But that force you push on the cart is acting on the cart, and the cart is pushing on you, which is acting on you. It's not really inertia that we are feeling, is mostly the acceleration we are feeling. So what makes roller coaster sometimes challenging to be, and like how astronauts need to be trained to deal with very large accelerations, is that feeling is the acceleration you're feeling. It's not the inertia that you're feeling. Does that make sense, Jacob? Okay. All right. I'll see you guys next time. Bye-bye.